Hey kids, time for a new unit. If you can see up in the top right corner, you might notice I got my COVID-19 haircut. It's the only one I was comfortable giving myself, so try not to get mesmerized by my beauty throughout this whole video. Okay, so chapter 5, it's all about trigonometry. This is a good one. I really like this. I like parabolas too, but trigonometry for me is super interesting. So we're going to have a look here. We're going to be expanding on what we did in grade 10. And let's have a look what's in store. So today, angles in standard position in quadrant 1. All right, so some basic things here. Instead of always thinking about angles as, oh, here's a triangle and here's an angle, or maybe here's an angle or whatever, we're going to think of angles a little more generally. This isn't just about triangles anymore, although there's going to be a relationship there. We're going to think about angles represented on a 2D plane, the Cartesian coordinates, the XY grid. We're going to start at the positive x-axis, and that's going to represent an angle of 0. We'll be showing this a whole bunch. Angles in standard position are measured from the positive x-axis. So what I'm saying here is, here's your xy coordinate grid. We're actually going to be measuring angles from here. This is like positive x. Negative x would be on the other side, and what we're going to be doing is we're going to be measuring angles from this direction. So instead of just having a random triangle floating out here, and maybe that's x, we're just standardizing everything, okay? So all angles are going to be measured from the positive x-axis. Positive angles get to be measured counterclockwise. So what I just sketched here, that is a positive angle. A negative angle will be measured counterclockwise. So this little arm here can spin in the clockwise direction. I think that's what I said. So that would be a negative angle. So this is a little bit maybe backwards to what you'd expect if you think clocks are the right way of running, but what we're doing here is when we go counterclockwise, this is positive x and positive y, so this line here has got a name, we'll get to that in a bit, but this line here is having like a positive x and a positive y, so it makes a positive angle. And when it dips down below, that's like negative y, so it's a negative angle. Anyway, it doesn't really matter, you can just remember. Okay, so we also have a naming system of quadrants. Some of you are familiar with this already. Quadrants 1, 2, 3, and 4. Roman numerals tend to be used, but they don't have to be. And they're labeled counterclockwise starting at the top right. So this picture here shows the first quadrant is up here, then second, then third, then fourth. Just memorize that. Pretty simple. Okay, an example would be to draw the following angles and state the quadrant they're in. So the way that we would draw an angle like positive 60, we would sketch a little Cartesian coordinate system here. I'm just going to put it right here, right here. And starting at this axis here, the positive x-axis, we're going to rotate, and we're going to rotate 60 degrees. Now here's 0. Just like always, full rotation is 360, so that would be 90, this would be 180, this would be 270. And then coming back here, you'd actually come back to 360. And you should put those little degree signs above everything. So a 60-degree angle is going to look something like this, and it's going to point up like that. There is 60 degrees. B would be negative 30. I might have to draw these a little bit smaller to fit them all in. So we're starting here and rotating down 30 degrees clockwise, and it's going to maybe look something like that. So there's negative 30 degrees. Keep in mind, this is negative 90 now, and we're trying to draw it going about a third of the way, right? So if you kind of imagine splitting this up into thirds, you don't have to be amazingly precise, but you should be fairly accurate. A 30 degree should not look like a 45. Okay, for C, 120, we'll sketch. It's positive, so we're starting at the positive x-axis like always. Same thing for this one. And we're rotating 120 degrees. That means we're going past 90, which would be straight up and down. There's 90. And we're going to 120. So we got to go 30 degrees past 120. So that's about a 120 degree angle. 180. Turns out positive and negative are the same thing. Doesn't really matter. So you're going to rotate all the way around like this, and then you would draw this line right here, and that would be at 180 degrees. So that's a 180 degree angle. And you could have even went the other way. Negative 180 would have given you the exact same thing. But we're talking about positive here, so there you go. Okay, for E, now at this moment in time, if you haven't given this a little bit of thought, maybe you want to pause the video and actually try it yourself. What does negative 250 look like? Pause it now and give it a shot. Okay, so what this would look like here is we'd be at 0. We're going negative, so we're spinning this way. If we spin halfway, that's 180, and we have to go an additional 70 degrees past it. So we'd be pointing maybe something up like that, and that would be negative 250. F, that's a bad y-axis. We are positive, so we're going to spin around. Now, if we go all the way around, that's 360, and we're going to have to do another full rotation. And yes, you would draw it kind of like this spiraling thing. So this is 0, but it's also 360. It's also 720. So we got to go to 770. So we're going 50 degrees beyond that, and this is going to go up, something like that. That's a 770-degree angle. And just for the record here, and this will be very important as we move on, this angle right in here, that's 50 degrees beyond 720. That's actually something called the reference angle, which will be very important later on. Anyway, so there we go. There's all our angles. Okay, the connection that this all has with trigonometry. So the terminal arm, that little thing I've been drawing actually has a name. That's called the terminal arm, and it extends from the origin all the way out here, and it ends at some point here, which is the terminal point. And if you think about this, this is kind of like it's located on a circle, because as this terminal arm spins around, it's going to trace out points on a circle. There's a much better picture of it. So the idea is that terminal point right here, terminal point P, so that can spin around in a circle. And now circles and triangles are actually very closely related. They don't at all look the same, but they're very, very related mathematically here. You can see as this moves around to some different position, you would draw your terminal arm going up there. And what you can do is you can always draw a triangle looking like that. People keep coming in my room, interrupting me. So the terminal arm is like the hypotenuse of a triangle. You always draw the legs of the triangle, those are the other two sides. They're always perpendicular, they complete a right triangle. So no matter how we draw this, there's the hypotenuse, and you would draw a leg down and a leg back over like that. Now you might be wondering, and this is actually fairly typical, is sometimes people will draw the terminal arm like this, and then they'll try and go over like that and down like that, and that's a sensible thing, but just by convention we never ever do that. One side of the triangle is always on the x-axis, and then the other side is the up and down, which connects it all together. So the adjacent side here is x. So whatever the coordinates of this point are, we always measure the adjacent side along the x-axis, and that has a value of whatever x is. So if your point was like 2, 3, then that would be x is equal to 2. And y is equal to 3. Awkward pause for wife coming in to nab my other computer. Okay, sorry about that. So the adjacent side is x, the opposite side is y, and that's a standard convention for everything. So no matter where we put the point on the circle, we can always say adjacent is x, opposite is y. And that means the adjacent and opposite can be negative. Okay, so, and of course this is the thing I was just saying, note the adjacent side is always on the x-axis. Always, always, always. Okay, so here's an example. The point 3, 4 is on the terminal arm of an angle theta in standard position. Sketch the angle. So this is now saying trigonometry, but just in a little bit of a different way. Okay, so we're going to think about it this way. We've got the point 3, 4. So if I just went like 1, 2, 3 here, and I went 1, 2, 3, 4 here, and I'd have a point right there. You don't have to draw a circle around it all the time or anything like that. Just understand that as this terminal arm swings around, this would actually kind of make a circle, but we don't have to draw that all the time. So what we do is we draw the terminal arm coming out. This we could call point 3, 4. If this is in standard position, it is possible to have non-standard angles, like something weird like this, where it's going up like that, and you measure the angle between the terminal arm and the y-axis. You can do that, but it's not standard. So when we say standard position, we're just talking about always from the positive x-axis to the terminal arm. Okay, so there we go. There's our angle. Pretty simple. B says determine the distance from the origin to P. This is actually a very simple thing. If you imagine here, just sort of resketching it, we've got this. This does form a triangle with 3 and 4. Right, here's our point P. I'm just redrawing it. How long is this distance along here? Okay, and this is a simple Pythagoras thing. What we would say is D, if we're going to call this D, the distance, d squared equals x squared plus y squared. It's just a Pythagoras thing. So d is equal to the square root. X squared is 3, y squared 4 squared. And of course, people familiar with the 3, 4, 5 triangle don't even need to do this, but we could say 9 plus 16 is 25. We're going to get 5. Okay, so this is not anything new or difficult. It's just a different way of asking Pythagoras. And the reason why we care about this is because if you want to know the length of the hypotenuse, that's how you can do it. Okay, C says determine the 3 trig ratios of theta. So what we formed in the last slide here, okay, we have 3, 4, this is 5, and here's our angle. So the 3 trig ratios, notice we're being asked for the trig ratios, not the angle itself. The angle itself is coming up in D. So what we'd say is we'd say sine theta, cos theta, and tan theta. Okay, so sine we know is opposite over hypotenuse, cosine is adjacent over hypotenuse, tan is opposite over adjacent. So what we would write for sine theta is we say opposite over hypotenuse, which is 4 over 5. And that's it. That's as far as we go. That's the sine ratio. Similarly, adjacent over hypotenuse would be 3 over 5. And opposite over adjacent would be 4 over 3. Those are the 3 trig ratios. Determine the measure of theta. Well, that would require us to use one of these 3 equations and use the inverse. So we could say theta equals inverse sine of 4 over 5. Or we could say theta equals inverse cos of 3 over 5. Or you could use theta equals inverse tan of 4 over 3. And they should all give you the same answer. They all equal, and this is where you're actually going to need a calculator here. I don't have one super handy, so let's see if I can jump over to this. Okay, well, don't worry. There's a reason for that. So we would go here and we would type in inverse sine. I'm just going to pick that one, and I believe it was 4 over 5. Is that correct? 4 over 5. Yep. So 53.13 degrees. So they'd all equal 53.13 degrees. And if you don't believe me, you can type in the other ones. They should all give you the same value. Okay. Here's another example. If sine theta equals 5 over 3 in quadrant 1, this is quite important, and you'll see why later on. In quadrant 2, it gets messier. 3 and 4, same thing. But let's determine cos and tan exactly. So we've actually done questions like this before, I believe. I think you might have even done some of that in grade 10. But let's just kind of imagine what we have here. I like to draw pictures all the time. If sine theta equals 5 over 13, and it's in quadrant 1, which is this one up here, what's our terminal arm going to look like? So this says our opposite equals 5, and this says the hypotenuse equals 13. So imagine a triangle where the opposite was the up and down. That was 5, and this had to be 13. If you drew to scale, that means the hypotenuse has to be a little more than twice as long as that. So that seems like that could be about right. There's our theta. How long is this side right here? So if we want, we'd have to say, and this would be useful because we need it for cosine and tan, we'd say x equals, okay, well, you know what, I have a hard time doing this. I want to write down Pythagoras first. X squared plus 5 squared equals 13 squared. Then I'm going to rearrange it. X squared equals 13 squared minus 5 squared. X is equal to the square root of whatever that is. So 13 squared is 169, this is 25, and it turns out that this is equal to the square root of 144, which is 12. Super. Okay, and some people might recognize another famous triangle, 5, 12, 13. 3, 4, 5 is a thing, 5, 12, 13 is another one. I think there's one like 8, 15, 17 or something like that as well. These are all the Pythagorean triples, and there's many more, but good to know something. Okay, so what we can therefore say is we could say cosine of theta equals adjacent over hypotenuse, so that's equal to 12 over 13. And we can say tan theta equals opposite over adjacent, which is 5 over 12. Okay, here's another one. Determine the value of sine 90, cos 90, and tan 90. I really like this because it actually forces you to think. If you go to a calculator and you try and type this in fact, we can just give that a shot right now. We can say, what is sine of 90 degrees? So we say sine of 90, and it says 1. And we can say cos of 90, and it says 0. And we can say tan of 90, and it says undefined. But that's not very fun using a calculator. Let's actually think about this. If we make a 90-degree angle starting from the positive x-axis, we're ending up right here, which means our terminal arm, and I'm going to pick a different color for this, our terminal arm is actually straight up and down. Okay, so now we have to think about this a little bit. What does this triangle look like? Normally we draw a triangle, you know, our terminal arm's out like that, we could do that sort of thing, but we can't really do that anymore. We draw up and then we kind of come back down. So what can we conclude about the three sides of this? Remember, the x-coordinate equals the adjacent, the y-coordinate equals the opposite, and the hypotenuse is equal to x squared plus y squared. So, well, what do we make of this? We'd say sine of 90 degrees equals opposite over hypotenuse. Now, how long is the opposite side? Imagine some point here. Okay, so let's pick a point there. And we say the point is at, what are the coordinates of this terminal point here? The x is actually very easy because it's 0. And y is, well, we don't know, but y is somewhere on that line right there, okay? So the point would be 0, comma y. What we can therefore conclude about the opposite side is the opposite side is y. We don't actually know how high it is, but it's y. Now what's the hypotenuse? So you can kind of logic this out, or you could do some math. Let's see, so if opposite equals y, and the adjacent equals x equals 0, then we could say the hypotenuse equals the square root of x squared, 0 squared plus y squared. Okay, this is a pretty mathematical and overly technical way of saying the hypotenuse is the square root of y squared, which is just y. Yeah, I know it's supposed to be absolute value of y, but we're not even going to touch that here because everything's positive in this case. Anyway, what we basically have is the hypotenuse is the same length as the opposite side. So the ratio of the two is equal to 1. Sine 90 gives you the ratio of how long the opposite is to the hypotenuse. And if the two are the same length, because think about it, this triangle goes up and then comes straight back down, the two sides are the same, which means the ratio is 1. So sine of 90 is 1 degree. We could similarly say something like cosine of 90 is equal to adjacent over hypotenuse. But the adjacent side is the x-coordinate, and that's 0. There is no this side to our triangle. It just goes straight up and down. So this is 0 over y. 0 divided by anything is 0, except for 0. And then finally, tan of 90 is opposite over adjacent. So the opposite side is y and the adjacent is 0. Well, what's anything divided by 0 in mathematics? That's undefined, okay? right, and finally one more question here. Let us find, I'll go back to red. So the point A, x comma 7 is located on the terminal arm, blah, 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 you can read. Okay, so let's have a look at this one here. We have the point A, it's x comma 7, it's got an angle of 30 degrees. So that means our terminal arm is coming off at an angle something like this. This is 30 degrees. And we know it's x comma 7. So we don't know what the x coordinates are, but we do know that the y coordinate is here, and that's 7. What are the coordinates of A? So we obviously know the y coordinate, but we need the x coordinate. How do we solve this? This is a very basic trigonometry problem. I think most of the challenge of this particular lesson today is just getting used to the different language and how this actually relates to triangles. So this is exactly the same thing as solving this. 7, 30 degrees, tell me what x is. So we can solve this really easily. Which trig ratio is going to do this for us? We've got the opposite side here, and we've got the adjacent side, so tan is going to be very helpful. So what we could say is tan of 30 degrees equals opposite over adjacent. Do the old switcheroo to solve this. It's good to do proper algebra, but the switcheroo works really well. Okay, so this is 7 divided by tan 30, so we'll just jump out here, and there's tan already, so we'll go 7 divided by, okay, it's not, it doesn't like that. Tan 30, and let me just erase this. Okay, so 12.12. Okay, so we'll say 12.12. Every time you do trigonometry, you should take a second, just think, does that actually sound reasonable? Does this distance here look like it's about 12.12? I think, yeah, it looks very reasonable to me. Determine the slope of the terminal arm. So the slope of the terminal arm here, I really like this question because it sounds weird and different, but it's actually got a really simple sort of result. And if you paid really close attention to the last intro video, you might have been able to even catch how to do this very simply. The long way of doing it is to say slope equals rise over run. So if you think about this as a line, and maybe it's a line going forever, what is the slope of it? It's rise over run, and we know what rise and run are. In this triangle, the opposite side is like a rise, so this is like opposite, but it's also like the rise, and the adjacent is like the run. So we would say it has a rise of 7 and a run of 12.12 dot 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 dot. When we work this out, we can go 7 divided by this number. We can go 7 divided by 12.12, and then we can do 0.577 would be our answer. But if I wanted to do this more precisely, instead of typing in 12.12 blah blah blah, I could actually say 7 divided by 7 divided by tan 30, because that's what it is, right? 7 over tan 30 is the length of x. So 7 over tan 30 is this. Now some of you are probably going, well, that's sort of weird. Can't I just simplify this a little bit? And you're absolutely right. This is better written as 7 over tan 30. That's a more precise answer. But remember, how do we actually do this? We divide, we can divide things, or we can flip and multiply. So I'm actually going to flip and multiply here. So I would flip the denominator, and if you do this, you can actually see those cross out. And lo and behold, the answer to the slope is tan. Tan of whatever the angle gives us the slope. By the way, that's 0.577. But the interesting point here is slope equals tan theta. That's sort of a kind of semi-formula for you. Okay, anyway, there's a whole smattering of questions. The section is mostly just getting used to some of the language, the ideas of the quadrants, and just how we can work out trig ratios from points on a terminal arm and all that sort of stuff. Hope that was helpful. See you later when my hair gets a teeny bit longer.